Hey guys, today we're going to be talking about circular motion and basically solving an example problem to help better our understanding of circular motion. So basically there are a few major concepts of circular motion that are very important to know. And the first major one is the magnitude of radial acceleration formula. And basically that formula is acceleration, the radial acceleration is equal to velocity squared divided by the radius. And this formula is going to be important in larger, more composite formulas in which you can apply this. And basically the next formula we're going to be talking about is the period formula. So in this formula, t is going to represent the time it takes the object to move once around the circle. And then we're going to set t equal to the circumference of the circle all over the velocity, where the circumference equals 2 pi r. R obviously representing the radius. And the final two formulas we're going to be talking about are Newton's second law, and the magnitude proportionality, basically inverse formula. So the first one, Newton's second law, is basically that here, one sec, let me get my brush here, is basically that the sum of the radial forces is equal to the mass times the magnitude of radial acceleration, which we talked about here. And basically, the other formula that's going to be important a little bit later is, it's not really a formula, it's just basically something that you should know. It's that the magnitude of radial acceleration is equal to the inverse of the radius. So basically, let's say you double the radius, the magnitude of the radius. If you double the magnitude of the radius, the acceleration will be decreased by half. So that's basically why you need to know this, and that's basically how it works. It's inversely proportional. So now that we've gone over all of the basic circular motion formulas, we can actually get into some practice problems. I found us a good example of a circular motion problem, and it's something that we can also relate to, being a circus ride. And basically, this problem gives us the task. It says, you are an engineer working for Six Flags. You have been assigned on a team to build a ride that will consist of a spinning drum of radius 2 meters. That's going to be important. When the ride reaches a period of 1.7 seconds, the floor should be able to be removed without the passengers falling. And basically, the task was to determine what characteristics of this ride would ensure that the riders will remain stuck, quote unquote, to the wall. And we were supposed to justify our answer quantitatively. Now, basically, if you don't know what quantitative means, quantitative data, it means basically just means data with measurement, with magnitude, not just describing something, having concrete mechanical data to support your thesis. And basically, we're going to be using those formulas that we just went over to determine this. So before we do anything, let's look at what we know. So we know that it's a radius of, oh, my bad, wrong brush. That's not the brush we want to be using here. So we know it's a radius of 2 meters. And we also know that it has a period, sorry, I should be using a period of 1.7 seconds until the floor is dropped. until the floor is dropped. And so we can basically draw a picture of this. So we have our wonderful circle here. Now, let's see if I can make a better one here. There we go. That's probably the closest we're going to get to an actual circle here. So, and then we have our radius of 2 meters. So with this information, we can calculate the circumference. So the circumference, as we mentioned before, is going to equal 2 pi r. And we're going to set pi equal to 3.14 for this case. And we know that our radius is equal to 2. So that's going to be equal to 12.57 meters. That's going to be the circumference that we're going to be working with here. 12.57 meters. So now that we know this information, we're left with the question of, so what speed will keep the people, quote unquote, stuck to the wall? So basically we need to think about what forces are going to be acting upon these people to keep them stuck to the wall. And basically it's going to be this centrifugal force is the force coming from the center of the circle pushing out towards the circumference. And this force is going to keep the people inside the ride. They're basically lined along the circumference. It's going to keep them from falling down or falling outwards. And basically, in order to calculate the speed that we need to reach, we're going to use an example of a ride called the Gravitron that actually works. And it's basically the same ride as this one. We're going to calculate the speed at which that one travels in order to find the speed at which this one needs to accelerate to in order to keep the people pressed against the wall in that 1.7 second period. So basically we're going to use a diagram of the Gravitron. The Gravitron has a radius of 7.5 meters, obviously a little bit larger than the one we're going to be designing. 7.5 meters. And it can travel at a rate, its good velocity is going to be 24 rotations per minute. And basically, if you convert that to meters per second, that's going to equal 18.8 meters per second. And we were also given the information by the designers of the Gravitron that it takes 20 seconds to reach its velocity. So that means it must have a rate of acceleration of 0.94 meters per second squared. So basically, now that we know this, we talked about before that inverse proportionality between the acceleration and the radius. So basically, now that we know our velocity for the bigger one, it's 18.8 meters per second. We're gonna sort of figure out what velocity we need for the smaller one, our Gravitron 2, I guess we're going to call it. That we're going to find the velocity we need for that ride to keep the people pressed against the wall. And basically, we're going to use some logic here. So we're going to say if the bigger ride, the Gravitron, has a radius of 7.5 meters, and the smaller one has the radius of 2 meters, then we're going to say that so 7.5 divided by 2 is 3.75 that's basically how they're proportional. So what we're going to go ahead and do is we're going to multiply 18.8 by 3.75. And that's going to get us our velocity of 70.5 meters per second, which is pretty fast. That is pretty fast. So basically, and we also need to accelerate to that in 1.7 seconds. So that is an insane speed. So our acceleration is going to need to equal 70.5 divided by 1.7. .5 divided by 1.7. And our acceleration is going to equal 41.5 about meters per second squared. So that's a very, just think about that. That's a very rapid acceleration. In 1.7 seconds, boom, 70.5 meters per second. And if you look at all this data, it actually makes sense. We took our original radius for the gravitron of 7.5 meters, divided it by 3.75 and got 2 meters. And at the same time, we multiplied our original velocity by 3.75. So if we relate this back to the proportionality concept that we talked about before, which basically that states when an object moves in a circle at constant speed, its acceleration decreases by half. When the radius doubles, the bigger the circle, the smaller the acceleration. That's basically the general rule. So the radial acceleration is proportional to the inverse of the radius, which clearly we can see here. So going back to the inherent question, what characteristics of the ride would ensure the riders will remain stuck to the wall? Basically, it would just need to reach the speed of 70.5 meters per second in the allotted time. So it would have to have the mechanical capability of going 41.5 meters per second squared, accelerating at that rate, which it's practical because it is a small circle. It's not like it's a big, heavy circle that needs a lot of power, a lot of wattage to get it moving. So this is practical. It's not impossible. And I'm not exactly the ride guru, but I have a feeling this would not be that hard to design given that the radius is 2 meters, which is not very large. So, in conclusion, we sort of saw this this inverse proportionality in action with a concrete example, and we sort of answered this interesting problem, this engineering problem, and and this this is a great example, and I hope this example helped better your understanding. It certainly did help my understanding of circular motion, and yeah, that's the video.